So earlier we started with the EIGRP routing protocol and we learned some good fundamentals about EIGRP, especially when we were talking about the topology table. We learned that only a feasible successor and successor will be there in the topology table. For a successor, the route should have a smallest metric. For a feasible successor, the route needs to satisfy the feasibility condition. We saw this earlier. What is feasibility condition? The advertised distance of this route should be less than the successor value. That is what written here in the bracket also here. If you see, the AD of the feasible successor must be less than the FD of the successor. FD means what? Feasible distance of the successor. Feasible distance of the successor. So any total distance is called as feasible distance, but total distance of the successor is what matters here. Feasibility condition is equal to advertised distance of that backup route should be less than the successor's metric, successor's FD. Only those routes will be there in the feasible successor. All the rest of the routes that did not satisfy feasibility condition won't be considered. So we can see here EIGRP is not really having complete topology table. It has got best route. It has got the routes that satisfies the feasibility condition. What about the rest of the routes? Will not be aware of it. So, though the name topology table is given to this, we will not consider it to be complete topology. It is only partial. So, the only protocol that has got the complete topology table is the link state routing protocols. Only those routes that satisfy the feasibility conditions are going to be seen in the topology table, which means EIGRP cannot provide you the real topology. The routing table will have the best routes for every destination. Now here is another example to understand the routing table, the topology table, and then the neighbor table. If you have a close look to this picture, you will understand that C has got two neighbors, A and B. And A is connected via E0, B is connected via E1. And now for this destination, the advertised distance, which is here, is 1000. That is what advertising. A is advertising 1000 to C. And the advertised distance here is 1500. So B is advertising 1500 to C. We are seeing the output on router C. Now for the router, there are two feasible distance. One is this 1000 and this 1000, which is 2000. Another one is this 1500 and 1000 here. So which is 2500. This way it is 2500 is the total. This way 2000 is the total. Now we all know it compares the metric and picks only the low metric path. So the low metric path is via E0 via router A. A is the gateway. So this is the elected path. Now, will this be a feasible successor? Let us check. Feasible successor. For feasible successor, the advertised distance, which is 1500, should be less than the successor value. What is the successor value? The low metric value. Of course, it is true. That is why you are seeing that in the topology table. Otherwise, you won't find this here. Let's say this one is 2100. If this is 2100, then you will not find this line here. Why? 2100 is not less than 2000. Please ask me a question if you have. Now EIGRP has got this 5 different packet. One, the hello packet which is sent every 5 seconds. This is the reason behind the establishment of neighbor. No? Every time it sends hello, if there is any new EIGRP router, it can learn about this router. Likewise, when that router sends hello, this router learns about that router. Not only that, to maintain the neighborship, the hellos are continued every 5 seconds. When the hello stops for 15 seconds, then the neighbor is considered dead. So hello is important. Next is update. Updates are sent in the initial interval, initial time. Updates are sent the initial time. When they form neighbor, the updates are sent. Updates from where? From the routing table. This router will send the routing table to that router. That router will send the routing table to this router. What do they have in the routing table? Their best routes. Their best routes are advertised along with their metric, which is called advertised distance for the receiver. Now, query and reply will come into picture when there is no feasible successor. When a successor goes down, usually it uses feasible successor from the topology table. But what if there is no feasible successor? It has to query the neighbors, the other neighbors. It has to query all other neighbors for that network which is lost, for which the route is lost. See, the primary route has gone down. So it will send a query to all other neighbors asking for the route to reach the destination. So that's query. For the query, if a router knows the path, if any neighbor knows the path, that neighbor will reply. Others won't. And then, when a query is received, acknowledgement is sent. When a reply is received, then also acknowledgement is sent. See, I am sending you a query. And you say, I got your question. You are saying, I understand. Okay, I got your question. That's the reply. That's the acknowledgement. That's not a reply. That's an acknowledgement. And then when you answer, after hearing your answer, I say, I got you. That's another acknowledgement to the reply. So acknowledgements are sent whenever update, query, reply is received. For the hello, we don't send any acknowledgement. Hello uses multicast address 224.0.0.10. EIGRP uses 224.0.0.10. So for the hello, there is no acknowledgement, but queries, replies, updates, or unicast, there is going to be a reply. I'm going to quickly do one small lab and show you before I move further. I feel that let's do a small lab, EIGRP lab, to see these 5 packets. I'll go to router 1 and put the IP address first. To know the interface name, I should click this G00. Alright, so we got 2 routers with the IP address. Next, what I need to do is I need to start the Wireshark to show you all those 5 packets. As of now, we see nothing, only layer 2 informations. Configuration test protocol. It's a reply coming from each router. It's like a keep alive that is going in between the switches. Some garbage data it is sending, like a ping message. Okay, now let's begin EIGRP configuration. I said router EIGRP needs autonomous system number. Let's put this 2 router in an autonomous system called 100. Router EIGRP 100. Next is, I'm going to say I want to run network 10.0.0.0, network 1.0.0. Now I should be seeing some EIGRP packets coming. Look at this. EIGRP packets are coming from 10.12.0.1, which is router 1. And if you open this EIGRP packet down here, it's an hello packet type 5. Opcode for hello packet is type 5. I'm going to right click and create a I want to create a profile for EIGRP. EIGRP profile. So for EIGRP profile, I want to increase the font size. Alright, I like this size. Alright, so next thing is I don't like this layout. I like this. Fine, now only hello packets coming from router 1 you see. What are things you see there? It's a EIGRP version 2, hello 5, checksum is for the integrity, checksum is good, flags are nothing, sequence no acknowledgement. Autonomous system number, you see? Autonomous system number 100 is what we gave there. And then if you go down, you can see the K values, bandwidth and delay. And then you can see the hold time for EIGRP is 15. The software version of EIGRP is 12.4. So we see all this info, but I'm interested in only hello packets. Right click, apply as a filter the selected one, and I'm going to create a button for this. Hello. Right, so now if I want to see only the hello packets, I can simply click this button. Only the hello packets will be shown. Right, so hello packets we know it's going, but so for no neighbor, because the other side is not configured. Show IP EIGRP neighbor, no neighbor. Show IP EIGRP interface, these are the interface running EIGRP. Let's now go to the second router. Configure router EIGRP 100, network 2.0.0.0, network 10.0.0.0. But before I hit enter, I would like to keep this like this. Alright, done. Neighbor has come, and I should be seeing those update packets now, all the packets. I want to stop the capture. I stopped the capture so that I can show you. So hello was now, earlier it was coming only from 10.1, now 10.2 also started saying hello with the same K values and versions and so on. And then EIGRP hello from router 1 also goes. Afterwards comes the update packet, because they know each other now. This update, it's sent to a multicast address. Opcode is 1. There is another update sent to a unicast address, which is also opcode 1. So I'm going to create a filter for this opcode 1. Update. So when I click on hello, it shows only hello. When I click on update, it shows only update packets. I have put to filter, but I don't like these colors. For hello, I would like to give different color. I don't want any of this. I want to create my own. So first let us go to hello and copy this. Opcode 5 is hello. Opcode 1 is update. So now what I do is I go to the colorization rule again. Hub code 5, which is hello. Next. What happened? What's there? This is update. Update is 1. So for the updates, I would like to give green background, which is already there, which was already there earlier, but now I want a creamy green and pure white. Maybe I need to increase the green background a little solid. Okay. And then for the hello, I would just like to give blue background. Same white font. Okay. But I have not applied it, so let me go back again, colorization rule, make a check mark of this. Done. So if you see here, you got blue in hello, hello in blue, updates in green. Now let's open acknowledgement packet. Acknowledgement. Hello is 5. For acknowledgement, why it is showing 5, which means it uses the same number. It uses the same number. Anyway, you can see from the bracket, acknowledgement. Acknowledge. A normal hello, acknowledgement is 0. So if you have any number in acknowledgement, it's an acknowledgement packet. It uses the same number 5. Anyway, we cannot see query and response here because we don't have such scenario now. So I cannot capture that. Now if you see the update, let's see what is seen in the update. Very first update I want to check. Update going from router 2 to router 1. Let's go down and see. Address family. So Vaisha cannot capture the entire payload. It will sometimes filter the informations, but luckily we have it here. You see, from router 10.12.0.2 to a multicast address 224.0.0.10, an update with subnet 2.0.0 is sent, because by default it will do summarization, and the prefix length is 8 in subnet mask. You can also see here. But why the next stop is 0? We need to check the next update. You see, it also sends the delay value, bandwidth, MTU, reliability, load, all these parameters in the update. Let's move on to the next one, going from 2 to 1. Even this time there is no next hop. Nowhere they send a next hop. So next hop will be learned from where the packet is coming. Packet is coming from 10.12.0.2, so they learn that as a next hop. So the next hop is not advertised by the EIGRP. It is learned when the packet comes. So these are the information that we get from here. So it was a good demonstration, I hope. The filters that I was using in the Wireshark, it will be more useful when we have many EIGRP neighbors. So you can easily filter out all the hello packets and see who is sending hello to whom. In our scenario, we just had 2. For that, you may not need that filters, but it is good to have those filters and see who is saying hello to whom, who is sending update to whom. In the real network, when you have Wireshark, it will be jumping like it will be moving like a river. The pages will move like a river very fast. Many packet will be captured and you will not be able to trace. But when you have filter in your Wireshark, in a small lab environment, when you create Wireshark and keep it ready, and when you connect your laptop to a big network, now you can use those filters to troubleshoot very easily. That's why I create filters for BGP separate, for EIGRP separate. For every protocol I have separate filters, so that next time when I sniff, I need to just click on that button and show the evidence for which is talking to whom, what update is sent between the routers, and so on. So for a network engineer, using tools like Wireshark is must to be an effective engineer. For easy troubleshooting, for topology discovery, mostly people use CDP, Cisco guys. But with Wireshark also you can discover topology. With Wireshark, we can also become a small attacker. Not to attack, but to understand the attacks. You can use the Wireshark and see how a sniffing tool can get information from a packet. So, though it is not a sophisticated sniffing tool, you will understand how the attackers are so easily getting the information to attackers. Fine. Next, let us get back to EIGRP. See, EIGRP, what happens is, what we saw just now is this. This is what I was showing you using Wireshark. The hello was sent to 224.0.0.5. Router A is sending, I am router A, who is in the link. And router B is now learning the neighbor. Router B learns A as a neighbor and send a hello packet. Hello, I am router B. Here is my update. Here is my complete routing information. So what happens now is, hello plus acknowledgement is going to come from A. I showed you hello plus acknowledgement. Hello with acknowledgement number. And then topology table is updated with the information that we received from B. And then A sends the update. B sends the hello plus acknowledgement back to A. That's it. So this is how two routers form neighbor and share the route updates. Do you have any question in this?
So the neighbor router will not send the whole routing table, no, but it has only the best route, no?
Correct. Only the best route. See, in the routing table, what you will have is only the best routes.
So here it says that here my complete routing information.
Yes, correct. See, that is what I said. What do you have in the routing table?
Best route?
Best route. Now what do you supposed to share? Best route.
Best route.
Best route is equal to routing table.
Okay.
In our case, when I sniffed and showed you, I showed you 2.2.2.2.
Yes.
Because that is the only one to advertise. There is no other network to advertise.
Okay.
From B to advertise, that was the only network in the routing table. The other network, 10 network, is already known to A. It is connected in between A and B.
Yes.
So you don't advertise that because it is directly connected. The only network it was knowing is 2.2.2.2. It was sharing 2 network with a mask of 8 because there is default auto summarization.
Okay.
So complete routing table and the best route are same.
Okay.
Now I also showed you the metrics that are shared along with the hello packets. Not in the update packet. Update packet, the metric for the destination is shared, but in the hello packets you saw the metric components, the k values. K1 is equal to 1, K2 equal to 0, K3 was 1, K4, K5 was 0. I showed you that in the hello packet. Also, when I showed you update, you saw the real bandwidth like 1500 meg, delay is like maybe 50, something like that. So we saw the metrics or shared in the hello packet, sorry, the update packet, the actual metric, the actual bandwidth, delay, reliability, load and MTU. They are shared in the update along with the network as an advertised distance. Next time when I do the lab, I'll show you much more details like advertised distance and so on. So we saw advertised distance there. If you rewind this video and see, you will see that. This k values means what? It means these things, like 5 parameters that EIGRP wants to use. K1, K3, K4, K2, K5. This is not in order, so I'm just, usually it is K1 bandwidth, K2 load, K3 delay, K4 reliability, K5 MTU. This is how it will be. Right. So this is the order. In algorithm, K3 means delay. You see, K3 means delay. The actual delay into, sorry, K3 is 1 into the actual delay multiplied by actual delay. K2 is load, means 0 multiplied by bandwidth. 0 multiplied by bandwidth is 0. K1 is 1 multiplied by actual bandwidth, let's say 1500. It's 1500. So if you see, in short, this is what our metric is. Because we are going to multiply a lot of things with 0. K2 is 0, which is load. And then K3 is 1. 1 into delay is delay. K2 is 0. 0 into bandwidth is 0. Bandwidth may be 1500. on the link. So the final algorithm is only this much. You don't need to break your head with all this confusing stuff. If you know this one, which is in the red color, that's what the metric of EIGRP. The slowest link bandwidth plus sum of delay is EIGRP metric. The slowest link bandwidth plus sum of delay. So EIGRP uses this 5 metrics. This statement is no more needed for us, but just I am explaining because it is there in the presentation. What is that? Before EIGRP, IGRP was also in use. IGRP is the earlier version of EIGRP, Interior Gateway Routing Protocol. Whereas EIGRP is Enhanced Interior Gateway Routing Protocol. So this IGRP, which is the older one, was using only 24-bit. For metric calculation, it was using only 24-bit. Whereas EIGRP uses 32-bit. IGRP uses 24-bit for metric calculation. EIGRP uses 32-bit. So how many is the difference? 8-bit. What is the value of 8-bit? 256. That is why they have written here, to know the EIGRP metric for IGRP, you need to take the metric of IGRP, multiply by 256, you will get EIGRP metric. If you take an IGRP metric and multiply by 256, you will get EIGRP metric. EIGRP metric calculation. The metric is equal to slowest link bandwidth plus sum of delay. What does this mean? That's what we are going to learn next. But wait, let me finish this. I was telling you EIGRP and IGRP are same protocol, but there is a difference. One, we saw the bit difference. The other one is IGRP is a class full protocol. That's why they have come up with this another protocol as a version, next version, EIGRP. IGRP is classful, EIGRP is classless. It's like RIP version 1 and RIP version 2. IGRP is like RIP version 1. EIGRP is like RIP version 2. Classless. Classful. So when you have a router running only EIGRP, another router EIGRP, but this router supports only IGRP. So what will happen, you know? You no need to do redistribution. You run EIGRP and IGRP here. You no need to do redistribution. The redistribution will happen automatically between IGRP and EIGRP. R3. Automatically it will happen. The redistribution will happen automatically because they both use the same metric. Only the metric bit is different. So automatically when EIGRP provides a route with metric, IGRP will divide it by 256, not multiply, because for IGRP it should be 8-bit less. And when IGRP provides a route with metric, EIGRP will automatically multiply it with 256. So what I am coming to say is, they are compatible. We no need to do any redistribution between these two protocols to make it compatible. They are by default compatible because both the protocols use basically the same algorithm. Only the difference is classful. Another one is the bits are only 24, whereas there it is classless, and in EIGRP it is also classless plus 32 bit. But this is not a topic to be spoken today. It's an outdated topic because no one uses EIGRP. When you have a very old router which do not have EIGRP, in our environment, then you may need to know what I said now. There may be like 10 routers that supports EIGRP. There are 2 routers that don't support EIGRP. It supports only EIGRP. In such situation, I want you to remember this, that there is no need for redistribution between these two protocols. Now we are going to understand the metric statement. What does that metric statement say? Is the default EIGRP metric is equal to the slowest link bandwidth plus sum of delay. Slowest link bandwidth plus sum of delay. What does that mean? What is that slowest link? We understand sum of delay. Sum of delay means what? Addition of all delays. Sum means what? Addition. Now what is that slowest link bandwidth? Look at this picture. Between A to D, I don't know where my pen is. Okay, here it is. Between A to D, you can go via B and C like this. You can also go via XYZ like this. Which one should we consider? For that, the slowest link bandwidth means what? 64 is slowest link here in this path. This is the slowest link. You should not take T1. T1 means 1500 kilobit per second. You should not consider 1500. You should see only the slowest link bandwidth. Plus, the delays need to be summed. 2000, 2000, 2000, 6000. That's the meaning of slowest link bandwidth plus sum of delay. Likewise, if you see the second path, the bandwidths are same everywhere, so you just take any one, slowest link bandwidth plus sum of delay, 2000, 2000. And again, delay is equal to delay in tens of microsecond. And no need to worry about this. I'm just giving you an idea how the slowest link bandwidth plus sum of delay matters. The calculation will be done automatically. More the bandwidth, less the metric. This I explained to you some time back. You see, this autonomous system is EIGRP only. Autonomous system number is same like EIGRP autonomous system number. So there is no need for redistribution, I told you. EIGRP metric, if you take and divide by 256, you will get EIGRP metric. EIGRP metric, if you take and multiply by 256, you will get EIGRP metric. The bit length is 24 bit for calculating the metric in EIGRP. In EIGRP it is 32 bit. See an example. In EIGRP if it is 1000, in EIGRP it will be multiplied by 256, which will be 256000. In EIGRP if it is 512000, you need to divide by 256, then you will get only 2000. Now, this is just an example. So this shows that EIGRP metrics are backward compatible with EIGRP. As I said, this is an outdated topic. So this chapter was giving us a very good fundamentals of EIGRP. EIGRP is Cisco's routing protocol, which uses a reliable transport protocol for providing the guaranteed delivery of update, and then it uses dual algorithm to provide the best path and also a loop-free classless routing. It's a protocol PDM, protocol dependent module, means for every network layer protocol you got a separate module. For the EIGRP, IPv6, IPv4, IPX, AppleTalk, Novel, for all this you have a separate module. So dependent on the module that you take, it's going to work. Next is EIGRP uses 3 tables: neighbor table, topology table, routing table. Routing table will have only the best route. Topology table will have the best and the feasible successor route, successor and feasible successor route. For that feasibility condition need to be met to be a feasible successor. The best routes will be in the routing table. The neighbor table will have only the established neighbors. EIGRP uses 5 K values as a metric: bandwidth, load, delay, reliability and MTU. But it considers only bandwidth and delay. The slowest link bandwidth plus sum of delay becomes the metric of EIGRP. And the EIGRP and EIGRP are backward compatible because basically they use the same metric for evaluating a path. Another difference is the bit size. You need to multiply 256 with the EIGRP metric to get EIGRP metric. The reason is for EIGRP it is only 24 bit. For EIGRP it is 32 bit. Right? Do you have any question?
Sir, I have a question here. So when we say slowest link bandwidth, so what exactly that means? Suppose if I have 1 Mbps link and 500 kbps link, so will EIGRP consider only 500 kbps?
Yes.
Okay.
Because if I send with the bandwidth of T1, which is 1500, all will go and get blocked here, bottleneck, because here only 64 kb, you understand? So when you consider 64 and send, this can easily process, this can easily process, even this can easily process. There won't be a bottleneck. That is why it considers only the slowest link bandwidth. So for EIGRP, don't say only in that place I got 64, I have upgraded in all other places. It's useless. Even if you upgrade the bandwidth on all other, between all other routers, that 164-bit 64 kbps link also need to be upgraded. Only then you will get complete speed between A and D via B and C. Because this is how it works. It takes the slowest link bandwidth. You saw me showing when it was sending the update, it was sending the bandwidth information, the delay information.
So is this a disadvantage or something to attack in EIGRP?
Oh yeah, of course. Yes, it is.
So when if we purchase a 1 Mbps link, then it will be ideal if we considering the 500 Mbps.
Yes, it is. Alright, so let us now stop here.